G'day girls. Alright, so for this video what we're going to have a look at is electron configuration. You would have looked at this hopefully last year in a little bit of detail. You would have looked at what's probably called Bohr electron configuration. We're going to look at that just to review it, and then we're going to move on and have a look at what's called subshell configuration. If you are asked for an electron configuration in a test, make sure you give the subshell configuration, so the one that we're going to look at a bit later on. The Bohr one we usually use mainly for like figuring out bonding, charges of ions and stuff like that. The idea is, though, that your electrons are arranged in shells that surround the nucleus of the atom. And each of these shells has a specific capacity of electrons. So the maximum number of electrons that can be held within a particular shell, we calculate using the formula 2n squared, where n is the shell number or the energy level of that shell. Main shell electron configuration shows the number of electrons in an atom's shells. It doesn't go into the same detail as the others, but we'll have a bit of a look at how it works. Alright, so if we look at the energy level, what we're talking about is like energy level, say, let's have a look at the diagram here on the left. That would be energy level 1, this would be energy level 2, this would be energy level 3, okay, or shell 1, 2, 3. Our capacity is determined by this formula, 2n squared. Okay, so n is that energy level there, so that is n. What we're going to do, we're going to square it, we're going to double it, that's going to give us our capacity. So if we look at this one, it's going to be 2 times 1 squared, which is 2 times 1, which is 2. So our first energy level here has the capacity for 2 electrons. The next one, we've got 2 times 2 squared, which gives us 8, so 4 times 2 is 8. The third one is 2 times 3 squared, which gives us 18. 2 times 4 squared is 32. Now what you would have looked at last year is pretty much the 2882 method for these. Now that applies for your first 20 elements. After that it gets a little bit trickier, and we'll have a look at that when we look at subshell configuration next. But let's say I want to find the electron configuration of some simple elements. So I'm going to have a look at, say, carbon, which is atomic number of 6. I'm going to have a look at neon, which is atomic number of 10. And I'll have a look at phosphorus, which, I hope I don't stuff this up, but I'm pretty sure that's 15. So what happens, we start filling from the lowest energy orbital, so from the closest one. Once that's reached its capacity, we fill out. Now, there's a couple of things when we draw these. We want to make sure that our electrons are in pairs. We also want to make sure that our electrons are as evenly spaced as possible, which sounds sort of contradictory, but I'll show you as we go through. So for carbon, 6 electrons, so I'm just going to use my marker and green dots to represent my electrons. 2 electrons in an inner shell, okay, 1, 2, in fact what I might do is make that a bit bigger, 1, 2, sweet, and then I'm going to have 4 within my next shell out. Now what we want to do is give these guys as much space as possible, so 1, 2, 3, 4. That gives me my 6 electrons. So in this case, my electron configuration is the number of electrons at energy level 1, and then the number of electrons at energy level 2. So the electron configuration for here is 2, 4. Neon, 10 protons, so an atom will have 10 electrons. So 1, 2, and then we start filling the next ones out. Now, I'm going to give them as much space as possible. So 1, 2, 3, 4. Need another 4, 5, 6, 7, 8. Alright, so that gives us our 10. So our electron configuration in this case is 2, 8. Alright, now this also, if we have a look at it, gives us our valence electrons. Okay, so if carbon's got 4 valence electrons, neon's got 8. Let's have a look at the final one. Phosphorus, as long as I've got this right as it being 15, I'm going to have 1, 2. Alright, then I'll start filling up the next one, so 1, 2, let's start doing it the way I did before. Keeping it separate, so 1, 2, 3, 4, 5, 6, 7, 8. I've got 10. I need to get to that 15 mark, so 5 and the next one out. So 1, 2, 3, 4, 5. In fact, let's get rid of that because that's annoying. All right. So that's what we call our Bohr electron configuration. And again, this one here would be 2, 8, 5. Okay. And again, we've got our valence electrons here. So you should be familiar with that. Let me pause. All right, so there's a few here for you to have a bit of practice of. You've got chlorine, magnesium, nitrogen. Have a go at those, okay? Also have a look at what the ions of chlorine and magnesium would look like. So I want you to actually draw these ones up. Bring them to class next lesson. We'll go through those before we go on. And then we'll have a look now at what is called subshell electron configuration. So your shells are fine, but your shells are actually broken up into one or more subshells or orbitals. So it works along the same premise that there's lower energy and higher energy subshells, and there's a specific order to how these actually fill. So the idea is that there's 4 types of orbitals. You've got what are called s orbitals or subshells, you've got p orbitals or subshells, d orbitals or subshells, or f orbitals or subshells. And your electron shells are basically broken up into sections, okay? So the idea is that an s orbital or subshell can hold 2 electrons, a p can hold 6, a d can hold 10, and an f can hold 14. And what they do is they fill in a specific order. So let's have a look at what order they fill. All right, so this diagram sort of gives you an idea of how they fill, but we'll write it out just so it makes a bit more sense. So this is the order. We fill our 1s, followed by our 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and then we keep filling through this sort of way. Okay, you will not go higher than, look, to be honest, if you get any higher than that, I'll be very surprised. Okay, most of the time we sort of stop around that 4p. So effectively what you need to remember is this whole 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then maybe 4p onto the end of it. Now, this order shows us how electrons fill our shells, okay? It works at the same idea. So we start filling from the 1s end. Once that becomes full, we fill our 2s. Once that becomes full, we fill our 2p. We fill our 3s, 3d, 4s, 3d, etc. until we've got the amount of electrons that our atom has. So let's have a look at an atom. Let's go with calcium, which is atomic number of 20. So therefore, it's going to have 20 electrons. What we're going to do, we're going to start at 1s. Now, S's can hold, let's change that. S's can hold 2 electrons. Okay, so that can hold 2. 2s can hold 2, 2p, so p can hold 6. S can again hold 2, p can hold 6, 2, 10, etc. So calcium, what we're going to do, we're going to start out at 1s orbital. Now, S can hold 2 electrons, so it's going to be 1s2. That orbital is now full. What I need though is another 18 electrons, so I'm going to start filling my next orbital out, which will be 2s. So 2s2, I've now used 4 electrons. I'm going to start filling my next one out. 2p, it can hold 6, it's going to fill that up. So now I've used 10, I need to add another 10 electrons. 3s2, 12 so far, 3p6, 18, now 4s2, it's going to fill that, 2, 6, 2, 6, 2, 2, so 2 plus 2 is 4, plus 6 is 10, plus the other 10 gives you your 20 electrons. Now, that's what we call our subshell configuration. Let's have a look at one that's not quite as full though. Let's go with something like fluorine, which is number 9. Okay? So, starting at the 1s orbital. Now I only need 9 electrons this time. 2 go into the s orbital. Cool. I need another 7. So 2s2. Yes, I've got enough to fill that. So 2s2. 1s2, 2s2. I've used 4 so far. I need another 5. So 2p. I've only got another 5 electrons. It's got a capacity of 6. It's not going to fill it. 1s2, 2s2, 2p5. Okay? So it's about basically just filling your electrons from the 1s until you've reached the capacity of electrons you have. Once you start getting to a few of your larger ones, you start getting a little bit more complex, and you start getting some exemptions. Now, this little abbreviation here, I'll talk about it for you when we get to class. That's basically just saying up until argon, all of your shells are filled. Okay? But let's say I went with something like number 26, which I'm pretty sure is iron. I'm testing my knowledge of the periodic table here, girls, because I forgot to bring one across when I came across. So, we can use little diagrams to sort of show how these fill. So, 26, we've stopped at argon, which was 18, which means I need another 8 electrons in here. So, my 4s orbital, we use an up and down arrow to represent electrons. That fills up, so this becomes 4s2. We then start filling out our 3D. Now it's got a capacity of 10, so 2 electrons can go into each of these. Okay, but we start off by just putting in 1 to each of them. Okay, so 1, 2, 3, 4, 5, 6. Okay, so this ends up being 3d6. So if I was looking at my expanded electron configuration for this, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, sorry about that, 4s2, and 3d6. That's my electron configuration. There are 2 exceptions to this rule, however, and they make chromium and copper have a slightly different electron configuration. Because if we look at chromium, we've got number 24, and copper's number 29. Now, when these fill their electron shells, what they actually want to do is make sure that each of these little suborbitals in your D shell have at least, or have an even number of electrons. It's just the way they do it, just accept it, this is how it works. So, what we'd normally expect is this to be 4s2, and then to fill through here. But it doesn't work that way, because if we did that, you'd have 1, 2, and then 1, 2, 3, 4, 5, which is slightly less stable. So what it actually does is it pinches 1 of your electrons from here and brings it across. Okay, might sound, oh sorry, I've put 1 too many in here. It pinches 1 from there and brings it across. So what we actually end up with is that in here, and it comes away from in there. Okay, so we actually end up with 4s1, 3d5. Now you'll see that that's different because if you look at iron, it goes 4s2, 3d6. Now our electron configuration for chromium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Okay, and that 4s1 being your key difference. Copper works in the same principle. Okay, so what we'd normally expect is for this to be 4s2, and because it's 29, this 3d to have 9 electrons. But it's going to do the same thing. One of the 4s electrons is going to come in to fill the 3d orbital to make it more stable. So your electron configuration for copper ends up being 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10.